Picture a laboratory deep in the night. Flames dance beneath glass vessels as vapors swirl upward, condensing into droplets that promise something extraordinary. An alchemist, sleeves stained with mercury and sulfur, peers into the crucible, where base metal slowly transforms its appearance. Is this madness, delusion, or the earliest stirrings of what would become modern science? For over 2,000 years, alchemy captivated some of humanity's brightest minds. Emperors financed it. Philosophers debated it. Practitioners died for it, and not always metaphorically. The promise was intoxicating. Transform lead into gold, cure every disease, and unlock the secret to eternal life. Today we dismiss alchemy as pseudoscience, a curious footnote before real chemistry emerged. But that dismissal misses something profound. Alchemy was never just about making gold. It was humanity's first systematic attempt to understand and manipulate the material world. And the line between its myths and realities reveals far more than simple delusion. Alchemy's birthplace was Hellenistic Alexandria, that spectacular collision of cultures where Egyptian craft traditions merged with Greek philosophy and eventually absorbed influences from Mesopotamia, Persia, and beyond. The word itself tells this story. Alchemy derives from the Arabic alchemia, which in turn comes from the Egyptian word chem, referring to the fertile black soil of the Nile Delta. But esoterically, chem meant something deeper, the dark mystery of primordial matter itself, the fundamental substance from which all things emerge. Our earliest reliable window into this world comes from Zosimos of Panopolis, writing around 300 CE in the twilight of the Roman Empire. What survives of Zosimos is a fragmentary, scattered chapters, excerpts quoted by later authors, and the prologue to a work on apparatus and furnaces. Yet these fragments reveal something remarkable. Zosimos wasn't writing fiction or fantasy. He was documenting practical experimental work, theoretical frameworks to explain observations, and the accumulated knowledge of earlier practitioners. Among those earlier practitioners was someone extraordinary, Maria the Jewess, who lived sometime between the 1st and 3rd centuries CE. Unlike the legendary figures often associated with alchemy's origins, Hermes Trismegistus, the mythical Democritus, Maria was a real person doing real experimental work. She may be the first non-mythical woman in history to publish scientific or proto-scientific works under her own name. Maria's legacy lives in every kitchen today. She invented the bain-marie, the double boiler that French cuisine still calls by her name. The principle was brilliant in its simplicity. Nest one container inside another, filled with water. The inner vessel never exceeds the temperature of boiling water, providing gentle, controlled heat. This wasn't just cooking equipment. It was sophisticated temperature control for chemical processes, something alchemists desperately needed. But Maria invented more complex apparatus too. The tripicos was a distillation device with 3 arms, allowing the collection of different fractions as substances separated by volatility. The keratakis was even more ingenious, an airtight chamber where materials could be exposed to vapors from heated substances below. Mercury or sulfur would vaporize, and those vapors would react with copper or lead suspended in a pallet above. When sealed properly, these devices created what we'd now call a controlled atmosphere. The term hermetically sealed comes directly from this alchemical practice. Here's what matters. Maria wasn't performing magic. She was developing experimental techniques, designing apparatus, and solving practical problems. The processes she described, heating, distilling, vapor treatment, were real chemistry, even if the theoretical framework used to understand them was incomplete. Zosimos credited Maria with understanding that metals possessed bodies, souls, and spirits. This might sound mystical to modern ears, but it represented an attempt to categorize different properties. What we call physical properties were bodies. Chemical reactivity might be the spirit. The fundamental nature that made gold remain gold was its soul. The language was different, but the impulse was the same one driving chemistry today: to categorize, understand, and ultimately control material transformations. Alexandria wasn't working in isolation. Knowledge flowed along trade routes. Chinese alchemical texts from roughly the same period show surprisingly parallel developments, including the use of ammonium chloride, a substance crucial to metal processing. The Silk Road didn't just carry silk, it carried ideas, and alchemy was among them. Why did intelligent, observant people believe metals could be transmuted? The answer lies in a theoretical framework that was remarkably coherent given the knowledge available at the time. Enter Jabir ibn Hayyan, the 8th century Arab alchemist, whose work would dominate alchemical theory for centuries. Jabir, often Latinized as Geber in European texts, proposed something that seemed to explain everything. All metals were compounds of mercury and sulfur, combined in different proportions and different degrees of purity. The logic was elegant. Start with Aristotle's 4 elements: earth, air, fire, and water, and his 4 qualities: hot, cold, wet, and dry. Fire is hot and dry. Water is cold and wet. Earth is cold and dry. Air is hot and wet. Every substance, Jabir argued, possessed these qualities in various combinations. Mercury provided fluidity and fusibility. It was cold and wet, giving metals their malleability. Sulfur provided combustibility and fixity. It was hot and dry, giving metals body and the ability to be calcined. Gold in this framework was simply mercury and sulfur, combined in perfect proportions and perfect purity, matured in ideal conditions deep in the earth. Lead was the same basic ingredients, but tainted, impure, or improperly proportioned. If you could break lead down to its constituent principles, purify them, and recombine them in the correct proportions, you wouldn't be creating something from nothing. You'd simply be completing what nature had left unfinished. This is crucial to understand. Transmutation didn't violate the laws of nature as alchemists understood them. It was working with nature. Ancient metalworkers had observed that vapors from heated cadmia could turn copper golden, creating brass. Mercury and arsenic vapors could whiten copper to a silvery appearance. If vapors could change the color and the properties of metals, why couldn't a more profound transformation be possible? The Mercury-Sulfur theory persisted because it was genuinely useful. It helped organize observations. It predicted certain behaviors. It gave practitioners a framework for experimentation. When Swiss physician Paracelsus added salt as a 3rd principle in the 16th century, he wasn't contradicting Jabir. He was extending the framework to encompass all matter, not just metals. Salt provided solidity and resistance to fire. Mercury provided volatility and liquidity. Sulfur provided combustibility. Between them, these three principles could, in theory, account for any substance's properties. But here's where things get philosophically interesting. There's been historical debate about whether philosophical mercury and philosophical sulfur were the same as common mercury and sulfur, or abstract principles that merely resembled them. Some texts suggest these were spiritual or theoretical entities, but recent scholarship by historian William Newman challenges this view. Examining the actual alchemical literature reveals that many practitioners did mean literal, material mercury and sulfur. They believed these substances could be further refined into purer forms, and that these refined materials could be used in transmutation. This wasn't purely abstract philosophy. It was experimental chemistry, operating under an incorrect but internally consistent theory. No different, really, than phlogiston theory or caloric theory. Wrong explanations that nonetheless guided productive research. At the heart of alchemical aspiration sat the Philosopher's Stone, known by a bewildering profusion of names. The White Stone, the Red Lion, the Powder of Projection, Azoth, the Orphan, the King, the Hermaphrodite. Hundreds of oblique references, each name a clue in an elaborate game of secrecy. What was this substance supposed to do? Three things, primarily. First, and most famous, it could transmute base metals into gold or silver, not by itself, but as a catalyst. A small amount of the stone could transform vastly larger quantities of metal. Second, it could cure all diseases. Third, and most profound, it could extend life indefinitely, serving as or helping to create the elixir of immortality. The creation of the stone was called the magnum opus, the great work, and descriptions of the process are maddeningly inconsistent. Different texts describe different stages, different durations, different materials, but common threads emerge. Many accounts describe the work proceeding through color changes: nigredo, the blackening; albedo, the whitening; citrinitas, the yellowing; and finally rubedo, the reddening. These weren't just metaphors. They described actual visual changes as materials were heated, combined, and processed. The process involved cycles of heating, cooling, distilling, and dissolving. Materials would be calcined, heated until they broke down to ash or powder. They'd be dissolved in various liquids. The solutions would be carefully evaporated. Vapors would be collected and condensed. The resulting materials would be ground, purified, and subjected to the process again, and again, and again. Some recipes called for repeating operations hundreds or thousands of times. Was this purely symbolic? Some scholars argue the entire alchemical enterprise was fundamentally spiritual, a metaphor for inner transformation. The laboratory work in this view was either secondary or purely allegorical. The death of Nigredo represented ego dissolution. The whitening represented purification of the soul. The final reddening represented spiritual rebirth. But this interpretation doesn't match what we know about actual practice. Real alchemists maintained real laboratories. They purchased large quantities of actual materials. They developed actual apparatus and techniques. Account books from medieval and Renaissance workshops show alchemists buying mercury by the pound, sulfur by the barrel. They weren't buying metaphors. The truth seems to be both and rather than either or. Many practitioners pursued both material and spiritual transformation, seeing them as parallel or even identical processes. The laboratory work was real chemistry, but it was chemistry imbued with symbolic meaning, performed within a framework that saw matter and spirit as intimately connected. Consider Roger Bacon, the 13th century English philosopher and Franciscan friar. Bacon discussed the philosopher's stone seriously, seeing it as a substance that could cure disease and extend life. Yet Bacon was also a serious experimental scientist, contributing to the development of optics and promoting mathematics and experimental methods. Was he deluded? Or was he working at the frontier of knowledge, where chemistry and philosophy hadn't yet separated into distinct disciplines? Even Isaac Newton, perhaps the greatest scientific mind in history, conducted extensive alchemical research. A recently rediscovered manuscript in Newton's hand contains detailed instructions from American alchemist George Starkey for creating Sophic mercury, philosophical mercury. The recipe involved repeatedly heating and combining mercury, sulfur, and silver. Newton didn't write about these experiments in his public work, but evidence suggests he performed them. Why would the man who formulated the laws of motion and gravity waste time on alchemy? Perhaps because in Newton's era, the line between chemistry and alchemy remained blurry, and the question of whether transmutation was possible remained genuinely open. While European and Islamic alchemists obsessed over transmuting lead to gold, Chinese alchemy pursued a fundamentally different goal: immortality itself. Gold was merely a means to that end, not the end itself. Chinese alchemy emerged from Taoist philosophy and its concept of the Xian, human beings who achieved immortality through holistic practices, including meditation, breathing exercises, diet, and, yes, alchemical preparations. The logic mirrored Western thinking in some ways. If certain substances possessed longevity, gold that never tarnishes, jade that endures for millennia, then consuming those substances might transfer that property to the human body. The most important substance was cinnabar, the red mineral mercury sulfide. Cinnabar's brilliant red color held symbolic power in Chinese culture, associated with the sun, fire, vitality, and the yang principle. More practically, cinnabar could be found in Chinese mountain ranges, particularly in Sichuan and Hunan provinces, making it more accessible than rare imported gold. The alchemical process involved roasting cinnabar to produce liquid mercury, that uncanny substance that flows like water, yet is clearly metallic. Mercury could then be combined with sulfur and heated again to return to cinnabar, the solid yang reformed from the liquid yin. This reversible transformation suggested profound possibilities. If matter could cycle between states, why couldn't the human body? The alchemist Ge Hong, writing around 320 CE, produced the Baopuzi, an enormous work that remains one of our best sources on early Chinese alchemy. Ge Hong provided recipes for gold, cinnabar, elixirs, and other preparations, along with recommendations for meditation, breathing exercises, dietary practices, and even methods for walking on water and raising the dead. This integration of laboratory practice with spiritual discipline characterized Chinese alchemy. External alchemy, called Weiden, and internal alchemy, called Naden, were understood as complementary paths. The preparation of Weiden elixirs was complex and ritualized. It wasn't just mixing ingredients and heating them. The alchemists followed strict rules of purification and seclusion. Ceremonies protected the work and the worker. Specific times and astronomical alignments were observed. The laboratory became a sacred space where material and spiritual transformation occurred simultaneously. But here's where the story turns dark. Mercury is extraordinarily toxic. So are many other substances used in Chinese elixirs: arsenic compounds, lead, realgar. The symptoms of mercury poisoning include tremors, cognitive decline, kidney damage, and eventual death. Yet countless people, including Chinese emperors, consumed these elixirs in pursuit of immortality. The first Qin emperor, Qin Shi Huang, died at 39, almost certainly from mercury poisoning. His tomb was designed with rivers of liquid mercury, and ancient texts describe his obsession with alchemical immortality elixirs. He's far from the only one. Tang Dynasty records document emperor after emperor, noble after noble, dying from elixir consumption. The physician and alchemist Sun Simiao, writing around 650 CE, acknowledged that mercury, arsenic, and sulfur were poisonous, yet prescribed them for elixirs in far larger quantities than for medicines. How could this continue? Tang alchemical texts show practitioners were aware of the dangers. A 9th century text lists 35 common mistakes leading to illness or death from elixir consumption. Yet the practice persisted for centuries. Perhaps some people developed tolerance to chronic low-dose exposure. Perhaps the symptoms of poisoning, tremors, visions, euphoria before the final decline, were interpreted as signs the elixir was working, that transformation was beginning. The scholar and poet Bo Juel, writing in the 9th century, was among the skeptics. He watched friends die from elixir consumption while he, never touching such substances, lived to old age. He wrote bitter verses about the irony. Cinnabar in the fire melted away. I could not save the young maid and stop my turning to a frail old man. Eventually, the deadly toll became impossible to ignore. By the end of the Tang Dynasty, external alchemy fell out of favor, replaced by Naden, internal alchemy. Instead of consuming external substances, practitioners would cultivate the elixir within their own bodies through meditation, visualization, and breathing exercises. The body itself became the laboratory, the crucible where transformation occurred. This was safer, certainly, though practitioners still faced dangers from extreme fasting, sleep deprivation, and altered states that could spiral into psychological crisis. The parallel with Western alchemy is striking. Both traditions started with material practice, laboratory work, actual substances. Both eventually moved toward more spiritual or psychological interpretations. But the Chinese transition happened earlier and more completely, driven by an undeniable body count that made the old way untenable. Strip away the mysticism, ignore the impossible goals, and focus on what alchemists actually did in their laboratories. The picture that emerges is of genuine technological and scientific progress. Start with apparatus and techniques. Alchemists developed sophisticated methods for distillation, creating apparatus that could separate liquids of different boiling points. They perfected sublimation, the process of turning solids directly to vapor and back to solids. They created reflux systems where vapors would repeatedly condense and re-evaporate, gradually purifying substances. These weren't trivial achievements. They required understanding heat transfer, vapor behavior, and material properties. Maria the Jewess's contributions alone would ensure alchemy's place in the history of technology. Her bain-marie revolutionized any process requiring gentle, controlled heat. Her karatakis, creating sealed environments where materials could be exposed to vapors, anticipated modern vacuum techniques. When German chemist Franz von Soxhlet modified the karatakis principle in 1879 to create the Soxhlet extractor, he was building on alchemical foundations laid 17 centuries earlier. That device is still used in laboratories worldwide. Alchemists discovered, or refers to describe, numerous substances. They isolated alcohol through distillation, calling it water of life. They discovered mineral acids, nitric acid, sulfuric acid, hydrochloric acid, substances of immense industrial importance. They identified new elements including zinc, bismuth, and arsenic. They developed improved processes for making glass, dyes, and metallurgical compounds. The discovery of distilled alcohol alone revolutionized medicine and chemistry. Medieval physicians used alcohol as a solvent to extract medicinal compounds from plants, creating tinctures far more potent than simple water-based preparations. Alcohol's properties as a preservative, solvent, and fuel made it invaluable. The mineral acids were even more significant. Nitric acid could dissolve silver. Sulfuric acid could dissolve iron. Hydrochloric acid could dissolve zinc. These substances made possible entirely new classes of chemical reactions and industrial processes. The development of aqua regia, a mixture of nitric and hydrochloric acids that could dissolve even gold, represented a profound achievement, even if it undermined the notion that gold was perfectly stable and unchangeable. Paracelsus, the 16th century Swiss physician, took alchemy in a medical direction that would profoundly influence the development of pharmacology. He rejected the notion that medicine should rely solely on plant-based remedies. Instead, he argued for using mineral and chemical preparations to treat disease. This was controversial. Using mercury to treat syphilis, for instance, often proved as dangerous as the disease. But Paracelsus's basic insight that chemical substances could be medicines helped establish iatrochemistry, the application of chemistry to medicine. Consider laudanum, the opium tincture Paracelsus developed. Dissolved in alcohol, opium's active compounds became a powerful painkiller and sedative. For centuries, laudanum was one of the most important medicines available, even though its addictive properties eventually became apparent. Paracelsus was applying alchemical principles, using chemical processes to extract and concentrate desired properties to create practical medicines. Many alchemists made important contributions to metallurgy. They improved techniques for purifying metals, for creating alloys with specific properties, for working with difficult materials. These advances had direct economic impact. Better metalworking meant better tools, better weapons, better construction materials. The knowledge accumulated through alchemical work also included safety information. Alchemists learned which substances were toxic, which combinations were dangerously reactive, which processes required ventilation. This practical knowledge, passed down through generations of practitioners, represented the beginnings of chemical safety protocols. When did alchemy become chemistry? There's no single moment, no clear dividing line. Instead, there was a gradual shift in how practitioners thought about matter and how they conducted their work. Robert Boyle, the 17th century natural philosopher, made crucial contributions to this transition. Boyle formulated what we call Boyle's Law, describing the relationship between gas pressure and volume. But more importantly, for chemistry's emergence, Boyle proposed a new definition of what an element is: the simplest substance that cannot be broken down into simpler components by chemical means. This seemingly simple definition was revolutionary. It shifted the focus from theoretical principles to empirical testing. You couldn't just declare that earth, air, fire, and water were elements. You had to demonstrate that they couldn't be decomposed further. And when you tried, you discovered they could be. Water could be broken down. Air was a mixture of different gases. The old categories collapsed. Antoine Lavoisier completed the revolution in the late 18th century. When Lavoisier demonstrated that water was formed by combining hydrogen and oxygen, he proved water was a compound, not an element. If water, the most fundamental substance in earlier frameworks, was actually composite, then the entire theoretical structure of alchemy became untenable. Lavoisier's 1789 treatise listed 31 substances he identified as true elements, substances that contemporary chemistry couldn't decompose further. The list included oxygen, hydrogen, nitrogen, sulfur, phosphorus, carbon, and various metals. Not all his identifications were correct. He included light and caloric as elements, but the approach was sound. Start with observation, proceed through systematic experimentation, accept only what evidence demonstrates. This empirical approach transformed how people thought about transmutation. Under the alchemical framework, transmutation was theoretically possible because metals were compounds of more fundamental principles. Under the new chemistry, transmutation would require changing the fundamental nature of atoms themselves. And atoms were by definition indivisible and unchangeable. The irony is that modern physics proved transmutation is possible after all. Nuclear reactions can transform one element into another by altering the number of protons in an atomic nucleus. Lawrence Berkeley National Laboratory used a particle accelerator to create gold from bismuth, though the amount was microscopic and detectable only by measuring radiation. Commercial nuclear reactors routinely transmute elements as uranium fissions into lighter elements. So the alchemists were right that transmutation was possible, but wrong about almost everything else. It requires conditions, extreme energies, nuclear reactions, completely inaccessible to anyone working in a medieval or Renaissance laboratory. And it's far too expensive to be practical for creating gold. The ancient dream of easy wealth through transmutation remains impossible. What then should we make of alchemy? Not a simple fraud or delusion, clearly. Not pure metaphor or spiritual allegory, though those dimensions existed. Instead, alchemy was humanity's first systematic, sustained effort to understand and control material transformation. Alchemists were wrong about their theoretical framework. Metals aren't compounds of mercury and sulfur. No philosopher's stone exists. Drinking mercury doesn't grant immortality. But they were right about something more fundamental. Matter can be understood, manipulated, and transformed through systematic investigation. Every time you use a double boiler, you're using Maria's invention. Every time a chemist distills a liquid or creates a vacuum seal, they're using techniques alchemists developed. The acids, the elements, the pharmaceutical principles all grew from alchemical work. Perhaps most importantly, alchemy established the principle that nature's secrets could be uncovered through experimental practice, not just passive observation, but active intervention. Heat this, combine that, measure the result, modify the procedure, try again. This iterative, experimental approach is the foundation of modern science. The alchemists failed to achieve their grandest goals. No one transmuted lead to gold, cured all disease, or achieved immortality. But in failing, they developed the tools and methods that made chemistry possible. In seeking the impossible, they discovered the achievable. And maybe that's the real philosopher's stone. Not a substance that transforms matter, but a method that transforms understanding. Not a powder that makes gold, but a process that makes knowledge. The quest for the impossible drove genuine discovery. The mystical dream catalyzed practical progress. That pattern, pursuing an impossible goal and discovering something valuable along the way, characterizes much of human endeavor. We don't always reach our declared destination, but the journey changes us and expands what's possible. So the next time you hear about alchemy dismissed as pseudoscience or fantasy, remember Maria and her Alexandria workshop, developing the bain-marie that chefs still use. Remember Jabir, formulating a theory that, while wrong, was sophisticated enough to guide centuries of productive work. Remember the Chinese alchemists who, despite tragic mistakes, developed techniques that influenced medicine for millennia. Remember that the line from their laboratories to modern chemistry is direct and unbroken. The transformation they sought was impossible. The transformation they achieved was profound. And in that gap between aspiration and accomplishment, between myth and reality, lies a very human story of curiosity, persistence, and the slow, difficult process of figuring out how the world actually works. If you enjoyed this journey through alchemy's fascinating history, please like this video and subscribe to the channel. There's so much more to explore in the history of human knowledge, and I'd love to have you along for future adventures into the past.